So I hope yes, I am now. Okay, I'm recording this. So you can look at it afterwards. I will put it on YouTube so you can see it. So we find the chemical which we have two of the quantities for. This one I can't do anything with yet. I forget for a minute. I go moles, that from that triangle, moles is concentration times volume over 1,000. So that equals 0.075 times the volume, 19.8 divided by 1,000. And this equals 0.001485 moles. Okay? So that's the moles of this chemical here. All right, so that's the first stage. The second stage, and often in the question, they will ask you specifically, they will say, find the moles of this one, then tell me the moles of that one, and so on. So now I can get rid of this. I have used this. I now know I have 0.001485 moles of permanganate. So what I have to find now is the moles of iron. To do that, I just look at the equation. The equation says one of these with 5 of those. So one of these with 5 is over there. So the moles of Fe equals 5 times this. Okay, so you work the moles of the first chemical, and then you look at the equation, and it says 1 to 5, so 5 times as many moles of the iron. That equals, you could do this on your calculator, but I'm just trying to show you, 0.007425 moles of Fe2+. Okay, so first stage, moles of permanganate. Second stage, look at the equation, 1 to 5 multiplied by 5. Okay? So now I know the moles of the iron, and now it says find the concentration. Well, concentration from our triangle, so I'm going to find the concentration, so the moles 0.007425. The triangle says okay, so I want the concentration. So the concentration is moles over volume over 1,000, okay? So concentration equals moles over volume over 1,000. So this can come up here, can't it? So the moles is 0.007425 over the volume, and we look back in the question, and here it is. Okay? So here is the volume of the iron. This is the moles of the iron, and that many moles is in this volume. So we want to work it out per liter. So it's this divided by 25 over 1,000. Bring the 1,000 up here. And the answer is 0.297. Now, if you got that, that's fantastic. Don't worry if you didn't. What I want you to do is just look at that question again later and just make sure you can do it, because it is practice that makes you get confident, okay? That is very important. This confidence comes through practice. I know you can do these now. Did Tumaini get that? Tumaini, is this okay or not? Tumaini. Ah, half and half. Okay, that's good. Sorry about the guy in the red jumper. Have a look at it afterwards. Genesis, is this okay? Excellent. Okay. Did you have a comment, Sophia?
No.
Sorry?
No.
Okay, good. All right. So have a look at that afterwards and make sure you can do it. Okay. I sent some work to you, which you won't have seen yet. It doesn't matter. Okay. It doesn't matter that you haven't seen it yet. The work, basically, it has a lot of questions which I have found for acids, bases, and salts. What I need to do is to find out what it is you can't do very well. Okay, this is very important to know what it is you can't do. So there are many questions. You will have seen them, or you may see them afterwards. I'm just going to show you them just very briefly. I'm not going to do them all now. I'm going to do some of them this week, some of them next week. I'm going to show you some bits and pieces. But firstly, I'm just going to make sure that you will recognize them when you see them, okay? So here they are, I hope. Whoops, not that. Not that. I hope, Sophia, can you see that, the equations?
Yeah, yes, I can see.
Good. Okay, everybody. This is the sheet here that we start with, okay? And the first thing that we have to be able to do is this technique here, writing an ionic equation. We will look at that, but I need you to think about whether you can do it. After that, down this page, there are many questions, many. They are all from KCSE. They are all examination questions about acids, bases, and salts, okay, all of them. There are too many to deal with in one lesson, many too many. Sometimes they are really simple questions, like this one here. This one here, this is a very peculiar question, and it is telling you that, it is telling you something about life. Here we are. It says here, we've got, whoops, hello. It says we have a beekeeper who was stung by a bee, and application, in other words, putting on a little solution of sodium hydrogen carbonate helped to relieve the irritation. Why? So it's asking for explanation. So sometimes it's that, sometimes it's a calculation, sometimes it's about strong and weak. Whoops, sorry, like this one. This one is about indicators. This one is about an indicator in a lab. And this is about strong and weak acids. So that is where we are going to go. So that's where we start. I'm going to start with something that I was going to show you last time, very briefly, because there is something you need to know about acids and alkalis and indicators. So I'm just going to use a different camera. I hope it works. Yes. I hope you can see now, over here now, I have some phenolphthalein, some methyl orange, and some full range indicator. And what I'm going to do is I'm going to just show you the colors that they go in acids and alkalis. So I'm going to add some full range indicator into this tube. What does that tell me about that chemical? If that is full range or universal, they are the same stuff. Universal indicator, full range indicator. This has gone, its normal color, you can see, is green. It has gone purple. What does that tell me? Somebody put on a microphone and just say out, is that alkali, neutral, or acid? Anybody? Okay, I'll tell you what, we will have a different way of doing it, okay? So I want you to put up your hand, okay? I want you to put up your hand, Genesis Tumaini, if you think it's the right one. So if you think that is acid, put your hand in the air, please. Okay, if you think it is neutral, put your hand in the air, please. Okay, if you, okay, some people think it's neutral. If you think it's alkali, put your hand in the air, please. Okay, so we don't know. Is that right? We don't know? Okay, well, I will tell you, that is alkali. Purple is alkali. In an acid, it goes red. So universal or full range indicator goes red in acid and purple in alkali. If you didn't already know that, you should write that down. That is very important, okay? So red in acid, purple in alkali. Now, methyl orange is the next indicator, and you have to know the colors it goes. This is, this is the same, this is alkali acid, alkali acid. Okay, so in the alkali, methyl orange goes that color. It doesn't look very different from this one. So in acid, it is pink, and in alkali, it is orange, okay? So methyl orange, in alkali here, this is orange, and here it is more pink, more red, okay? Phenolphthalein, so that's methyl orange, okay? Phenolphthalein, whoops, sorry. Phenolphthalein, very difficult to spell, is also an indicator. And in alkali, it goes this purple-pink. But in acid, it stays colorless. So we will write those down just in case people don't remember them, but it's very important that you know those, okay? So I'll write them down now. I will write them, sorry, Fatma was just trying to get in. I will now come back to my camera and we'll just make a note just so we know what colors they go, because that's very important. So, what I'm going to do is I'm just going to make sure that we've got that as a list. So the indicator, the first one was full range, which is universal. It's the same stuff, okay? Universal, full range, the same, okay? In acid, this goes red, orange, or yellow, depending on the strength of the acid, okay? Very strong acid, weaker, quite weak. In alkali, it goes purple, or violet, or blue. You need to know those colors so that you can go, ah, yes, that is alkali, that is acid, no problem. There is a problem with this universal indicator, and its problem is that it changes a lot. So it goes from red to orange to yellow to green to blue to purple, many, many different colors. It's really good. It's really good for many things, but for titrations with burettes, it's useless. The second indicator is methyl orange. Methyl orange. Many of the KCSE questions use methyl orange. Methyl orange in acid is the same as this here. It is red. In alkali, it is yellow if there's only a small amount, or orange. That seems like that is small difference, but when you are doing a titration, it's actually quite easy to see the difference. The last one is phenolphthalein. It is difficult to spell. That is quite a name. Phenolphthalein in acid is colorless, but it is pink in alkali. Okay? That is something we need to know, all right? That is something we need to know. Okay. So I'm just going to go to camera. Just a moment. No, I can't. There's a technical problem at the moment. I'll come back to that. Okay, so you need to remember these because they ask questions, and we're going to go through the next, which is about what acid and alkali is. So, can anybody tell me what an acid is? How do we define acid? Anybody tell me? Can anybody write down what an acid is and show it to Michael or Dan or Fatma, please? I need to know what an acid is.
It is a proton donor.
It is a proton donor. Yes, it is a proton donor. Good. Can anybody tell me? Good. Was that somebody from Genesis? Okay. Can anybody tell me the difference between a strong and a weak acid? Do you know this already? Do we know the difference between strong and weak acid? Michael, Dan, Fatma, can you ask people? Tell me whether you think that they. Tell me what they tell you. What's the difference? Yeah, okay. So Genesis is okay. Tumaini, are you confident with the difference between strong and weak acid or not? Are you confident? Not confident. Confident? Okay, excellent. Okay. What does an alkali produce? If acids produce protons, what do alkalis produce? Anybody? They all produce one thing in water, alkalis do. No? Okay. In which case, what is the definition of an alkali? An alkali does something to an acid. What does an alkali do? What is the definition? Bronsted-Lowry definition. Anybody? Come on, Genesis, you got your ties on. You should know. You're very clever. Come on. Come on, Tumaini. It's getting warmer in there because we're losing jumpers. Come on, let's have somebody tell me.
It is a water-soluble base.
It is a soluble base. You're absolutely right. It is a soluble base. Good. What does a soluble base do to an acid? What is the definition of what is the definition of an alkali, a soluble base? What does an alkali or a base do to an acid? It does something for an acid. Anybody?
it neutralizes the acid.
It does neutralize it. It does neutralize it. How does it neutralize it? There is one phrase that you need to know. An alkali, it's a proton acceptor. Did you know that? Do you know proton? Acid is a proton donor, you know that. Did you know an alkali is a proton acceptor? Do you know this? Yes? No? It's important because we need to talk about it if you don't. Okay. Tumaini, do you know alkali is proton acceptor? Yes? No? No? Okay, all right. Okay, let's have a quick look at that very quickly. Here we go. All right, the first thing is, if I have an acid like hydrochloric acid, here, hydrochloric acid, when it is in AQ, in water, it splits up. But it splits up reversibly. So it splits up to make H plus and Cl minus. The next acid also does this. This one is an alkanoic acid. This one is ethanoic or ethanolic. Whoops. Or acetic acid, and it does the same thing. In other words, it splits up, both of them split up to produce this. This is what makes it an acid, proton donor. This is the Bronsted-Lowry definition. Okay? So both of them produce this. So how come the pH, and remember how you write pH, pH is small p, capital H, because the H is for hydrogen, okay? So if I look at the pH of these, this is about 1, and this is about 3. So why is this, for the same concentration, why is this a pH of 1, strong acid, and this one 3 or 4, much weaker? This one is used in food, yeah, for pickling, for putting on foods and so on, tastes slightly sour. If you put this one on your food, your teeth will fall out. Okay, poof. Okay, so we put this one in food, but not this one. So why is this one stronger than this one? Anybody tell me, why is the one at the top, hydrochloric acid, a strong acid, but ethanolic acid is a weak acid? Why is this? Anybody? It's something to do with this. It's something to do with this reversible reaction. Can anybody help me? Anybody help me? Shall I just tell you? I'll just tell you. It's a long day. You finish school, I'll just tell you. Okay. This reversible reaction means that the HCl splits up and the H plus Cl minus join together. And they do it simultaneously. They do it at the same time. Some splits up, some joins together. But most of this acid is split up. So if I drew this, I could draw it like this. Almost completely this way. This one, almost completely this way. Now, we know what this means, but you're not allowed to write it in an exam. So what we say is that this one is fully dissociated and this one only partially dissociated, okay? So the word that we want to use is dissociated. Split up, okay? This one is 99% split up. This one is 1% split up, okay? So hydrochloric acid, 99% of all the HCl are split up, 1% are not split up. This one, ethanolic acid, 1% split up, 99% not split up. It is the H plus, the proton, which tastes sour, that has the pH, okay? So it is the H plus which we taste, which the pH is, it's what reacts with metals and so on. So if there are many H plus, it's very strong acid. If there are very few, mostly they are caught up in here, they are stuck in here, it's very weak. Okay? Is that okay? Genesis is okay. Tumaini, are you okay? Or cool. Thank you for the guys at the back. Well done. Okay. The same is true for alkalis. Okay. So here this is recorded anyway. I will send it to you. But the same is true of alkalis. So a strong alkali is sodium hydroxide. Sodium hydroxide is a very, very strong alkali. It's very hazardous. They use it for making soap. We will come to that. We use it for making soap from oils and fats and so on. And it splits up to make OH minus and Na plus. And this is a strong ammonium hydroxide, also splits up, also forms this. This is the same. But this is weak alkali. This is a weak alkali. So strong alkalis make lots of this OH minus. Okay, lots of OH minus. This strong one, pH 13, 14. This one, pH 10. Okay, so this one is very strong. And this one is 99% split up, dissociated. This 1% not split up. This one, the other way around. This one, 99% not split up, only 1% split up. Okay? So that is why. So the word to use is dissociated. Acid or alkali, same thing, dissociated. So we can put that all together to say one thing, and this is it. Okay, so strong ones dissociate almost fully, weak ones hardly split up at all. So I'm going to write that down. So strong acid or alkali, or acids or alkalis, are nearly fully dissociated. Split up. Okay, that's very important, that idea. It's one that you will need to remember. And weak acids or alkalis are only dissociated partially. Partially means only a little. Okay. All right. Okay. So let's see why acids and alkalis are put together in equations. So what I'm going to do now is I'm going to just look at the equation for an acid and an alkali reacting, and we're going to see if it's okay. All right? Rude. Okay. Okay. All right. Now I'm going to look at an acid and an alkali reacting together. Now, if we look at an equation like this, this is hydrochloric acid, sodium hydroxide makes sodium chloride and water. Okay? Now, what I want to do is to turn that into an ionic equation. I'm going to try to share a screen with you now. I'm going to see if I can do it on this. It would be better if I can do it on this. Okay. Sophia, if you're there, can you see the white screen?
Yes, I can see it.
Okay.
With the rubber. Yes,
Yeah?
I can see it.
You can see it. Okay. So we have HCl, AQ, plus NaOH, AQ, goes to NaCl, AQ, plus H2O. Whoops. To H2O. When we do an ionic equation, what we do is we look for all the chemicals which are AQ, okay? All the AQ ones split up. So what we do is we find the cation and the anion, okay? Now, cation and anion are two words that we use quite a lot. And I hope you know what cation and anion are, but I'm just going to show you something. A cation is a positive ion. Now, the positive ion, oh, good heavens, what have I written there? Come here. Come on, pick up. Oh, come on. Try again. Right. Positive ion. Okay. One of the ways to remember this is to write this like this. I teach my students if I write a plus, not a T, so the word is cation. But if I write it like this, I remember plus ion, positive ion, okay? And then anion is negative ion. Now, the point about this is that if you can remember that the cation, the T is a plus, it makes it very easy to remember A plus ion. So the cation is the positive one. Okay, that's really important that you can remember that. Okay, so I'll go through that again in a bit, but that's the basis. Okay, so what I do is I look at my equation and I split it up into the cation and anion. And what I do is this. I say, anytime it's AQ, I split into two. AQ, split into two. AQ, split into two. Liquid, no split. Okay? Then I go back to the first one, HCl, and I know it's going to be H plus, which is AQ, and Cl minus, which is AQ. And the NaOH will be Na plus AQ. You should know Na, it always is Na1 plus, and OH minus AQ. This turns into NaCl is AQ, so it splits up Na plus AQ plus Cl minus AQ. And, this doesn't split up, so this is just H2O. Now, this looks horrible. This looks really, really complicated. But what I do is I look for anything, like in maths, like in mathematics. If we find something on both sides of the equations, we can get rid of it. So I'm going to get rid of my Na plus here because here it is here. And you can probably see I can get rid of the Cl minus because that is here. Now the rest I can't change. So now I write the equation out again with only the bits which haven't changed. There is that, there is this, and there is that. So it comes out as H plus AQ plus OH minus AQ goes to H2O liquid. And this is what you said, neutralization. But if we look at it in a slightly different way, this came from the acid. So the acid is a proton donor. You said that. And the OH minus grabs the H plus. They hold on to each other to make water. So the OH minus comes from the alkali up here, and the alkali is a proton acceptor. And so the whole thing is neutralization. Okay? So let's just look at that again. Okay, so I'm just going to look at it all again, just to make sure it makes sense. I'm going to pick a different acid and different alkali, but I'm just going to see whether this makes sense and we can do it again. Okay, this is recorded, so you will be able to see it again, but let's look at a different one. So here we go. I'm just going to move this up. I'll leave it there so anybody who is still writing can see it. Now I'm going to write again. So this time I'm going to have a different acid. I'm going to have H2SO4, AQ. And I will have a different alkali, KOH, AQ. This makes the salt K2SO4, AQ, and H2O, liquid. This is not balanced. If you remember from last time, when we look at balancing an equation, we look for the number of hydrogens and the number of sodiums. Potassium works the same as sodium. So two of these, one of those, I need two. The two here, 2K there, that's good. SO4, SO4, and I've got two of these. Now, I do exactly the same again. So what I do is I look for the ones which are AQ, okay? So the AQ ones, this will split into 2. And this AQ will split into 2. And this will turn into, this is AQ. So this will split into 2. This one, no, liquid. Oh, hello, what happened there? Doesn't matter. That was meant to be L in brackets. Okay, so this one, L, not AQ, does not split. So back to the beginning. H2SO4 splits up into H plus, but there are 2 of them, 2H plus, AQ, plus SO4, you probably know this, SO4 is 2 minus. And the 2 KOHs split into 2 K pluses and 2 OH minuses, both AQ. This turns into this, which is AQ, 2K plus AQ, and SO4, 2 minus AQ, and not split up. So 2 H2O liquid. Now, if you look at this, I think you will be able to see which ones we can get rid of. Okay, we look for which are on each side. So here's the equation, left and right, left side, right side. So we're looking for ions which are on this side, and on this side we can get rid of. So here's K plus, 2K plus, 2K plus. SO4, okay, so SO4 2 minus, SO4 2 minus. Then I rewrite the whole thing underneath, only with the ones which are in the whole equation. So there's that, and that, and that, which means the equation is 2H plus AQ plus 2OH minus AQ goes to 2H2O liquid. We could divide this by 2. We could make it H plus OH minus goes to H2O. That's fine. That would be fine too. But there's nothing wrong with this one. This one is okay. So let's go just back up to the top, to the other one. I'll leave this one on in just a minute, but I just want to go through what happens, because the other one is a bit simpler, a little bit easier to look at, okay? So I'm just going to go back up to the top, then I will come back to this one. So we had HCl at the beginning and NaOH. Anything that is AQ splits up. Anything which is L or S or G does not split up. We split them up. Each one of the AQs split up. The one which is not AQ does not split up. We then get rid of these, which are on both sides of the equation. We call these, you probably know this, spectator ions. Like at a football match, spectator, watching, not doing anything. The 2 chlorides here, not doing anything. Na plus, not doing anything. Spectator ions. We then just write out with the bits which are left, H plus, OH minus, H2O. Here is the equation. So this is what we call the ionic equation. If we now look at the other one, here it is, a bit more complicated, but the same thing happens. Let me just push it down a little bit, so we're only looking at the simple bits to start with. So here it is. Here it is. Okay, I'll just get rid of the top one here, just so it's not in the way. There we are. Okay, so here it is. H2SO4 AQ, that will split up. 2KOH AQ, that will split up. K2SO4 AQ, that will split up. 2 H2O liquid, that won't split up. So I split them up. Come on. Ah, don't die on me. Thank you. So I split them up. H2SO4 splits 2H plus, SO4 2 minus. 2KOH, 2K, 2OH. K2SO4, 2K, SO4. So I put them all down. Then remove the ones which are the same on both sides, the spectator ions. And then I'm left with 2H plus, 2OH minus, 2H2O. So that is the equation. Come on. There, at the bottom. Okay. All right. Okay. So that's recorded. So if you want to see it later, it's there if you want to see it. I'll put it up right at the end in case anybody missed any bit. That is called ionic equations. How many of you feel okay about writing, not that kind, but ionic equations generally? Are you okay or not okay with writing ionic equations? People at the front, okay. People at the back of Genesis and Tumaini, are we okay with ionic equations or not okay? Okay, most people are okay. Okay, thank you very much. That's very useful. Thank you, gentlemen in the front of Genesis. Okay, so what we're going to do next time is we're going to look at some experiments, okay? And I'm going to show you a little one now just to see what we are actually doing and writing equations about. But in the sheets which you have, in these sheets here, what I would like you to do first with these is to turn these into ionic equations, okay? Turn these all into ionic equations. And then it says, and describe what you would observe, okay? Describe what you would observe. Let me just show you why that's important. Quite often the question comes up, can you write, sorry, no, let me just remove that just for a minute. Here we are, here are the equations. And what we're looking for is, can we see anything in these where something happens which we could see, okay? Something that changes. Because sometimes you will see something, here we are in D. Here we are in this equation here. Something happens that means we could see something. And the something we could see is this, G. That means we would see bubbles of a gas, okay? The next one down, something different happens. Here we have a solid. That means a solid forms. We start with AQ, they will look like water. We add them together, they make something that looks like water, salty water, but here is a solid, okay? So you are looking for observations. Let me show you two observations now, briefly, because I know it is time to go. Here I have some copper sulfate. Okay? This is a solution of copper sulfate. It's just blue. You can see against my lab coat, it is just blue. And when I add ammonium hydroxide to it, what happens is that the ammonium hydroxide seems to do nothing. Seems to do nothing. Nothing. Wait a minute. Something is happening. I hope you can see that this is not, as it was before, clear, transparent, but this is a precipitate. This is a solid forming in here. The next one is better. So what we're going to do is to try to write equations, because this is from one of the questions, KCSE, it talked about what is happening in this. The next one, this is lead nitrate, okay? Lead nitrate, very toxic, not very nice. So here is lead nitrate. It looks like water. I am not going to drink it. It is toxic. Here is some potassium iodide. Potassium iodide also looks like water. This one is not toxic, but something odd happens here. Watch, don't turn away. How? I turn water and water into yellow paint. This I can't see through. It's opaque. I can't see light through it. So two things that look like water make this. That is weird. Even I have been teaching chemistry for 40 years, and I have done this many, many times. I still think it is very, very weird. I'll show you it again because it's so weird. Watch. Too strange. Water. We know it's not water. More water. No cheating. Nothing clever. I am not hiding anything. Look. Here we go. Boom. Wow. That is crazy. This is precipitation. The yellow solid in here is lead iodide. Okay, lead iodide. In this, we would write an ionic equation which would show this as being something new. That is crazy. I think you think that's crazy. I hope you think that's crazy. I think that's crazy. Okay, so what we're doing next time is I want you to try to write the ionic equations for these first ones. If you want to look at any of the other questions, I will be sending to the supervisors, I will be sending the answers to all of them, okay? I will send all of the answers to the supervisors, not today, because I have to write the answers out, but I will send the answers. Now, what I want you to do is to concentrate on one thing at a time. So there are many questions about strong and weak alkali acids, which we did today. Dissociation. What I would like you to do is to look through and find all the questions which are about strong and weak and answer those, because if you can do those, you will be okay. All right. Each one is like 2-3 marks. It's very important you can do it. Okay. But now we are going to go. So I'm going to take my yellow paint and I am going to go because today I don't work in school. Tomorrow, yesterday, but today I don't work in school. So I have to go and do some carpentry. So I will leave you to do some chemistry. Okay? Do these first. Have a look at them.
Asante.
Asante.
We've enjoyed the magic.
Magic is magic.
Yeah.
See you guys.
Bye.
I hope you found something useful to do, Yestin.
I was listening attentively.
Yeah.
Bye-bye.
You're an Egypt if you did.
Egypt.
Egypt. Spell E-J-O-T.
Take care. Bye-bye.
See you guys.
Thanks.
Cheers.
Bye-bye.